I will attempt. I will foolishly attempt to be my own cameraman today. We'll see if it works. I think it'll work. I will begin with a word of prayer. So, that's right. You've been naughty. I will begin. Dear Heavenly Father, we thank you for this day. I just pray that you'd help us use this time wisely, just to cover a few of the rudiments of complex integration. In the name I pray, Lord Jesus. Amen. So I was trying to write things out on the board last time, and it occurs to me that was dumb because I have like 200 pages of notes prepared for complex analysis. Why didn't I use those? What's wrong with me? This is one stupidity begetting another. Anyway, so we can define the complex integral. That's not really what we're after in here today. Let me skip ahead here. I actually worked through this one last time, right? This is the integral. And this one kind of tells you a lot about what's going on, but here we have the integral of z minus z naught to the m. It works out to 2 pi I when m is minus 1, and otherwise it's 0, right? That's kind of interesting, and that sort of is an indication of things to come. It's the reciprocal powers that lead to non-trivial integrals. Now, let me plug my computer back in before it dies. So this, well, I'm not trying to teach you complex. Let me try to go ahead here. So, you know, some things, just to give you a quick rundown here, though. This example is kind of important. If I was going to integrate dz over z squared plus 6, and gamma r is the half circle of radius r, going from r to minus r on the real axis, then if you look at the modulus of the integrand, you can bound it by 1 over r squared minus 6, right? So if you look at that, then that gives me an m, and by the so-called ML theorem, we have the bound times the length of the integral. So the length of a half circle is pi r, right? And the interesting thing about this bound is what happens as r goes to infinity. It goes to 0, right? So the integral over dz over z squared plus 6 goes to 0 as r goes to infinity, which means, well, that's going to be important in the examples I'll show you from a little bit later on here. So that's one thing. Now, there is a complex fundamental theorem of calculus part 2. If you have a primitive, in other words, if the derivative of big F is little f, then and this curve gamma goes from point A to point B, this is the integral. So I mean, that's what could be nicer. So here's a stupid example. If I was to integrate, youch. Let's see here. Feel better. Don't tell the book buyers. I'm selling that thing. Let's see here. Where are we? Oh, yes. So I lost my laser. This guy. Now, what this notation means, and this notation is only reasonable if the function actually has an antiderivative, right? If I've got something that's got a pole, then this notation could become ambiguous if there's like a path dependence towards the integration. But this notation is not ambiguous, provided that the integrand actually has an antiderivative, and this one does. So it's like, pretty much we could teach this in Calculus 1, right? It's just with complex numbers instead of real numbers, but really, like, if you just kind of took the deeper theory out of it, it's nothing that we couldn't teach to high schoolers, really, you know? Now, this one's a little bit more interesting. 1 over z, all right? It has a primitive, which means antiderivative in the language of the book I was paralleling here, mirroring, of log z, which is the natural log of the modulus of z plus I times arg of z on c minus. Now, c minus is the complex plane with the negative real axis removed. It's a slit complex plane. And so if you consider the unit circle, curses. Somebody get the camera. I have, at this point I realize I've reached the limits of my... So what I'm talking about here is sort of a, like this, and you see there's a, so this circle goes, it's almost the whole circle. It goes all the way to pi. So this is at pi, but this one is at, what was it? Oh yeah, minus pi, plus, really should be minus epsilon, right? I think that should be minus epsilon. And then as epsilon goes to 0, those kind of become the full circle, right? And so you could approach the whole circle in a limiting process as epsilon goes to 0 there, right? And so I could, but anyway, for any finite epsilon, I can integrate over gamma epsilon, which is, where does it go from? I'm sorry, I'm trying to think where it starts and where it ends. It ends at e to the I, so it goes like this, right? And you see what's happening is the derivative of log z is 1 over z everywhere except this, and you can make this ray go everywhere you want. That's the kind of quirky thing. This is everything except for that is what's called C minus. It's the slit complex plane. It's missing this ray out to infinity, but everywhere except for there, the derivative of big log is 1 over z. So you have to play around. You can't cross this if you're going to use if you're going to use the logarithm in a curve in integration. Then you can't cross the curve of integration. Can't cross that. If you're going to use log as the antiderivative, that wouldn't be kosher, so to speak. But on the other hand, this one doesn't cross it, right? It goes from gamma minus pi minus epsilon all the way over to pi, never hits the bad part for the log function. And so this is a legitimate antiderivative for 1 over z on this not quite whole circle for arbitrary small epsilon. And so I can use fundamental theorem of calculus, and that gives me this minus that, which works out to 2 pi I, and that's supposed to be minus I epsilon, I think. But you see what happens as epsilon goes to 0, what do you get? 2 pi I, right? Now that would be a basic example of the residue theorem I talked to you guys about last time. See, because this function, 1 over z, has a singularity if you close the circle, right? You close the circle, and you look at f of z equals to 1 over z. Well, the residue at z equals to 0 of 1 over z is equal to 1. And the residue theorem says because the gamma is a counterclockwise oriented closed curve, which encircles just that one singularity at 0, the integral works out to 2 pi I times the residue, which here is 1, and that's why we get 2 pi, taking the limit as epsilon goes to 0. Okay. I'm going to stop majoring in the minors here and zoom ahead a bit. Well, I have examples which just basically exploit that idea further, but so this is the Koshi integral formula, which ultimately leads to the residue calculus. Let me just go ahead, zoom ahead here. Although I could conceivably, I could see a question on this exam you're going to take that might be just about knowing this formula. So let's stare at it for a second. The Shoshi's generalized integral formula. Are you taking complex right now?
I took it 2 semesters ago.
Ah, curses, we lost our chance. Did he do that? No, it's not in his nature. Now, technically, I mean, this is not quite legitimate, but if you go back to the Cauchy's integral formula, so Cauchy's integral formula says that if we integrate f of w divided by w minus z, provided that f of w is analytic inside this closed curve boundary of D, all right? So D is like a disk or something. It's a simply connected region of the complex plane. If f of w is well behaved in and relatively close to D, then we get this Cauchy's integral formula. And then the neat thing is, actually, if you could remember this, which if in the case that f is just 1 and that z is equal to 0, this simplifies down to 1 is equal to 1 over 2 pi I integral of dw over w, which is the example we just went over, for example. But more interestingly, if you differentiate this thing, you could differentiate this with respect to z, what would happen? If you imagine differentiating this with respect to z, if you pulled the z inside the integral, if you could commute the order of differentiation, then that would give you access to a formula that, what would happen when you differentiate? Well, I have it down here. If you differentiate f of z, just bring the d dz inside, questionable, but you can do it. That would give you this, right? So there's the connection between the derivative of f and the integral of f over w minus z squared. And then you can keep doing this, and doing this, and doing this, and that gives you the Cauchy's generalized integral formula, which is really kind of shocking. It says that there's some connection between the mth derivative of f and integrals of f divided by something which is divergent. It's a very strange formula, really. It says that there's some sort of connection between differentiation and integration that's not present in the real case. All right, anyway, I must go on. One of the useful identities that you obtain from Cauchy's generalized integral formula is the following. If I'm integrating f of z, suppose f of z is analytic inside this region, and if I have division by z minus z, z naught is a point inside boundary D, then this integral just works out to 2 pi I times the mth derivative of that divided by m factorial. So this means I can integrate expressions like this by just differentiating. What? That's very, very weird, is it not? Here's an example making good on that. But again, I need to move it along here. Yeah. Fun stuff. Power series. Yeah, I spent a while developing power series. It's great. Come on. Come on. If I was smarter, I would have looked at the table of contents, right? Sorry, it's too late. Laurent is interesting. Laurent was actually, as best as I could figure, Laurent was like I think he was an engineer or something kind of surprising. But I think he gave his work to Koshi, who had this to say about Laurent's work in the report to the French Academy of 1843. The extension given by M. Laurent seems to us worthy of note. I mean, it's like, it's a beautiful, it's completing the work that Koshi started. I mean, like, this way of thinking about it is the way we think about it calculationally today. No one calculates with Cauchy's generalized integral formula. It's horrible. Residues are how we actually do calculations in complex analysis. And really, residues are a clever reformulation of those theorems about Cauchy's theorems. So let me get to it. Let me actually get to it. So this is what the Laurent series decomposition says. If you've got a function, all right, which is analytic on an annulus like that, between an inner and an outer radius, then you can decompose f as a Laurent series, where the coefficients are related to the integrals, as you might expect from Cauchy's generalized integral formula. And so this says it's possible. That's basically, again, this is still not what I'm after. I'm sorry, guys. Come on. So many neat things in this book, but they're not what I want to talk about. Here's what I wanted to show you guys, in part. Nope, that's not it either. Dang it. I'm sorry, guys. Like, we knew that already. You didn't have to say it. So that's just me talking. All right, finally. Residues. So the residue of 1 over z minus z naught at z naught is 1. The residue of 1 over z minus z naught to the n at z naught is 0. Okay? This function, I've previously used partial fractions to rip this apart into z minus 1 over 2i, 1 over z plus i, plus 1 over 2i, z minus i. All right? So this will have 0 residue at every point except for 2. 2 points where it will have non-zero residue would be plus or minus I. Those are where it has singularities. If there's no singularity, if there's no like division by 0, you won't have a residue. Residues have to do with sort of misbehavior of the function in some regard. So this gives me a residue of 1 over 2i at I. See that one? And minus 1 over 2i at minus I, because that's the coefficient of the 1 over z plus I term. Now, the other pieces, the other pieces are just, you know, the thing is, if we center at I, then z and 1 over z plus I, these are functions which make sense if you plug in I, which means that if you do the calculus, those expand as a Taylor series centered at I. But the Laurent just cares about the reciprocal term, all right? And the reciprocal term, it's all just there, say, considering I. There are some trick formulas. Probably good for us to look at another example. This one, again, partial fractions gives you this. This has non-trivial residues at 4 and minus 1. And those residues are both, well, one of them's this, at 4 you get 1, at minus 1 rather, you have 1/5. And so I went to the trouble of doing all these partial fractions decompositions earlier in these notes, and now I'm just reaping the rewards of it, okay? Calculating residues by the partial fractions decomposition. Here's a more interesting one. Sine of z over z to the 6th. So what that means is you multiply the power series for sine times 1 over z to the 6th. Well, that gives you 1 over z to the 5th minus 1 over 1/6 z cubed plus 1 over 120 z. So this function has, well, this has what's called a pole of order 5, all right? And it has a residue of 1 over 120 at 0. At points other than 0, this is just analytic. So the residue anywhere except for 0 would just be 0. Now, Cauchy's residue theorem says that if you want to integrate a function over some region like that, over the boundary of the region, then what you do is you do 2 pi I times the sum of the residues at misbehaving points of the function. So all you have to do is find the points inside boundary D where the function blows up, where it's got a division by 0 or something like that. And if you can find a finite number of those, and they have to be isolated. Like if you've got a whole circle of infinities, we don't have technology to fix that. They have to be isolated singularities. But there's a whole bunch of theorems about those. And so here are the kind of nice simplifying formulas. If rule number 1, if f of z has a simple pole at z naught, then the residue you can get from just multiplying the function by z minus z naught and taking the limit as z goes to z naught. It doesn't seem especially useful, but it is. All right. And the proof is really simple to understand. If it is a simple pole, it looks like that. If you multiply this by z minus z naught, then you get a to the minus 1 plus z minus z naught times a, analytic function. As z goes to z naught, this goes to 0, and you're just left with a minus 1, which is the residue. It's pretty simple, really. This is the next. If you had a double pole, then you multiply by z minus z squared. Then you differentiate it and take the limit. All right. That will. So the proof is, again, just a straight calculation with the Laurent decomposition. You take the assumed form of f, multiply by z minus z naught squared. It gets you to this. When you differentiate, that pulls down the a to the minus 1 and other stuff that limits to 0. So there's the double pole rule. You might guess there's a triple pole and a quadruple pole, and there are higher rules, but I usually just find myself using. Actually, we use rule 3 a fair amount in calculations. So if I have f over g and I'm calculating the residue, and I need that g has a simple 0, that means that the 0 is not repeated. So something like, how to say this? X squared plus x would have a simple 0 at 0. Because x squared plus x, I can factor to x times x plus 1. The fact that it's just got x there means it's a simple 0. It's just, in contrast, f of x equals x squared has a double 0 at 0. So it's simple 0 means there's just one copy of the factor. It doesn't have any multiplicity. And so if you have that, then, so if g has a simple 0, you can calculate the residue by just taking, and we also need to know that f is analytic at z naught. Then you can just calculate it by taking f of z naught divided by the derivative at z naught. That's very nice. Here's an example of that. Sine z has a simple 0 at z naught. Since g of pi, which is 0, but g prime is not 0, this is how we actually quantify simple 0 with calculus. It means that the value of the function is 0, but the value of the derivative is not 0. A double 0 would have the function and the derivative both 0, but like the third derivative could be non-zero. That would be a double 0. Okay. So if the function at the point is 0, but the derivative at the point is non-zero, it's a simple 0. And sine has a simple 0 at pi. All right. So when I'm calculating the residue of e to the z over sine z, since sine z's got a simple 0 at pi, I can just plug in pi to e to the z, which is, by the way, analytic everywhere, and divide by cosine of pi, because that's the derivative of sine. And so there you go, that's the residue, e to the minus pi. Now, when you think about direct calculation of the residue here, it's quite awful, because you'd have to think about taking the power series for e to the z and dividing by the power series for sine of z, and then coming to terms with what the 1 over z term is and all that. That seems unfun. So these rules are very important for actual calculations. Let me get to some actual calculations, though. So here we go. Integrals featuring rational functions. This is a pretty typical trick. What we do is we integrate, whoa, sorry, I was splashing myself. Integrate over this half circle, right? This half circle is a closed contour, counterclockwise oriented. And, well, it's got two pieces. It's got this half circle, and it's also got this line segment. The beautiful thing about the line segment is that makes contact with real calculus. See, because this, and on the other hand, this integral should be equal to 2 pi I times the residue of the function, whatever singularities there happen to fit up in this half circle. So I get the following. I get the integral from minus r to r, f of x dx. This is an ordinary garden variety calculus 2 integral, right? Then is plus the integral over this half circle. Right, that's weird, but there are tools we have to put it into submission. And that's equal to 2 pi I times something I can just straight up calculate. This is amazing. This formula is fantastic. Here's how it works. We don't care about the proof. We want to see how it works. Here's an example. So to calculate, now this one's kind of a silly example because you can do this integral by other methods anyway, right? If I ask you to integrate from minus infinity to infinity of dx over x squared plus 1, what do? I mean, this has, what's that? Inverse tangent, right? So the answer is pi over 2 minus a minus pi over 2, right? You may not have heard what the bounds were. Minus infinity to infinity. The infinity contributes pi over 2, but then I've got minus inverse tangent of minus infinity, which is minus pi. So the answer is pi.
Oh.
Yeah. But here's why, from a complex perspective. So the limit as r goes to infinity of that will be equal to 2 pi I times that. Why? Because the other piece, the piece over the half circle, vanishes by the thing I showed you earlier. Because we can bound this by, I haven't written it down, curses. Well, I think I proved it in general up here, that if you've got 1 over, if you have something like this, then it can be bounded as r goes to infinity. So the piece over the half circle will vanish for a proper rational function, provided that the degree of the denominator is at least 2 or more than the numerator. And you see, the singularity I contributed, the minus I was outside the half loop, so it didn't contribute. Now, another example, 1 over, now this one starts to give, I mean, this integral, I would be more challenged to do from calculus 2, right? Like calculus 2, if I ask my students to integrate dx over x to the 4th plus 1, I'm not being friendly, right? I mean, that's nasty. I'm not sure we have the technology to do that in Calc 2. But here, if I want to integrate, what I do is I just integrate 1 over z to the 4th plus 1. See, the half circle piece dies because as r goes to infinity, that piece goes away. And we're just left with 2 pi I times the residue of this. Well, there are 2 singularities, this one and that one. We talked about these today in the abstract, actually. I think. Well, I'm sorry, we had a minus 1 rather than a plus 1 there, right? So these are a little bit different. Yeah. But it's kind of the ones we did, but rotated. But I digress. So these are the places where z to the 4th plus 1 is 0. And so 2 of those fit inside this, and those 2 give you a residue in particular of, and so what am I doing here? I'm calculating the residue of that. And I think what I did was, I used rule 4, which I didn't discuss with you guys. Sorry. But if you look at it, I'm just differentiating the denominator and plugging in the point, right? So it's kind of a special case of the one I did talk about. But there's your residues, and there it is, pi over root 2. Oh, look. Wolfram alpha can do it without complex analysis. There's the antiderivative for you, right there. Obviously, right? So pretty clearly, complex analysis is helpful. Now, you can also do integrals like this, where you have p of x over q of x times a cosine. All right? And there's another bag of tricks for that. Let me go on here. So this example, I'll just tell you what it says. Here I'm able to show that the integral from minus infinity to infinity of cosine over x squared plus 1 is pi e to the minus a. And the integral of sine a to the x over x squared plus 1 dx is equal to 0. Although I think that's actually the, well, anyway.
Pretty sure that cosine.
Oh, good. Now, lest you think that this is only useful for integrals from minus infinity to infinity, there's another game that you can play. You can do integrals of trig functions by looking at integrals of the appropriate complex functions around the unit circle. This is a really neat trick. So the idea is this. On the unit circle, we have z equals e to the I theta, which is cosine theta plus I sine theta, right? So z bar would be e to the minus I theta, which is cosine theta minus I sine theta. So, of course, we can solve for cosine theta, and we can solve for sine theta in terms of the imaginary exponentials, but that's also looking like z plus 1 over z and z minus 1 over z, right? So then we can use the residue theorem. Let me show you an example. So here, this integral, right, d theta over 5 plus 4 sine theta, I can look at that as the integral around the unit circle of dz over iz. dz over iz is d theta. 5 is 5, easy enough to understand. 4 is 4. Nobody's lost there, I think. Sine theta, I over 2, times z minus 1 over z. Notice the minus here. That minus is to put the I upstairs. And then I clear out the 1 over z by multiplying by z. Oh, there's z upstairs. So I multiplied that through. And that gave me dz over 2z squared minus 2z plus 5iz, which, because this is an example out of a book, factors ever so nicely. See? Voila. And then you can see that that has problems at, this has problems at minus I over 2 and minus 2i. So you're going to have singularities there and there. Only one of these matters to the problem because only one of those is inside the unit circle. Which one? Yeah, the I over 2 minus I over 2. So this is actually equal to 2 pi I times the residue of my integrand at minus I over 2, which is easy enough to calculate. It works out to differentiate this and plug that in. So you get 2 pi over 3. Is this also in your paper?
I made it pretty fresh.
Oh, okay.
Isn't that Fresno?
Fresnel or
That's more or less kind of the ones.
maybe. I'm not a. Here's a general version of that one for integral from 0 to 2 pi of 1 over 1 minus 2 p cosine theta plus p squared. Just works out to that. This is a. But anyway, anytime you do an integral for a variable, with a variable in it, of course, that increases suffering. The other kind of integrands you can do in complex analysis are integrals with branch points. That was kind of like this thing. I mean, that's exactly what this was. This was a branch point. So in other words, we're kind of avoiding some branch. And so to do that, you use these keyhole contours. What you do is to make a simply connected region, you just work your way around the singularity, go back along the thing you can't cross, and then I'm doing it up. Oh man, what the world? That's really it's a mind bender right there. So that one, dang it. Anyway, this is why I can't have nice things. Let's see here. So, oh man, I did it. Well, these are very questionable contours. I'll say that. As I was telling my other class the other day, this is why we need sabbaticals. So here's an example of one of those. If I take x to the a over 1 plus x squared, where a is between minus 1 and 1, then I can look at that as this right here as being the restriction of the z to the a over 1 plus z squared function. And I'm using log sub 0. Log sub 0 makes the angle jump for the logarithm at 0 rather than pi. So log sub 0 works on standard angles from 0 to 2 pi, which means there's a discontinuity for the log function along the positive x-axis. You can choose any set of standard angles you like, and you can move that angle deficiency from whatever ray you want to if you study this carefully. So log sub 0 is my thing, which doesn't behave well at the positive x-axis, but everywhere else is analytic. And anyway, after much suffering, you're able to show that this piece goes to 0, and the epsilon piece goes to 0, and I think maybe the L minus goes to 0. I'm a little rusty here. But after a bunch of reasoning, it basically just drops out everything except for a residue and the integral you're interested in. So it's this very sneaky, here's the details. This goes to showing that the R piece goes to 0, I believe. This goes to showing that that piece goes to 0. So you're just left with the integral over L plus, which tends to that integral, and this tends to that integral, and the sum of those two, I think, is going to be equal to the residue, and times 2 pi, and I've lost something here. Well, anyway. Oh my. So, I'm sorry, I have not done it justice. So it's this. Actually, the lower integral picks up a phase factor. That's the interesting thing. And so when you solve for the integral, you get 1 over 1 minus 2 pi IA, which after dividing the top and the bottom by that, produces a sine. And that's how we get pi A over sine pi A. And then Gamelin uses complex analysis magic to extend the result much further. But, ow! Schmarts. Anyway, the tricks for complex integration theory are really endless. There's about a dozen standard problems. I've shown you a few of them. There are fractional residues. You can have something like this. If you have a singularity that's on the edge of your domain, you can like half circle include it like that. And take the limit as epsilon goes to 0, it picks up half the residue. If you had a thing so that it was like at a sector, it would pick up the appropriate amount of the sector that it would, it's kind of the, I don't even have the words for it, but here it is. If Z naught is a simple pole of F, and C epsilon is an arc of angle alpha, then the result as epsilon goes to 0 is alpha I residue. So in particular, if alpha is 2 pi, we get this standard residue theorem. But this says that it's actually extends or descends perhaps to arcs. Oh my goodness. Let's see here. Another thing, this might actually matter to you guys, possibly. The principal value is something we can define and that calculus students sometimes calculate without realizing. So the principal value of an integral is defined to be the limit as r goes to infinity of minus r to r f of x dx. So, for example, if you have an odd function, the principal value is automatically 0 because you're integrating an odd function about a symmetric interval about the origin. So at every step of the game, that's 0, right? In contrast, if you integrate an odd function with respect to the standard notion of integration, the integral to infinity and the integral to minus infinity have to separately and independently converge to say that the integral converges. So a good example of this would be like, I don't know, I'm trying to think. Everything I can think of diverges at 0. But you're actually calculating the principal value with these calculations usually. Anyway, I think I've shown you enough to you have a flavor for it. Here's another example with 6 singularities, 3 of which are inside. Ooh, that one's fun. And then Jordan's lemma. You need something fancier to deal with stuff like sine x over x. Our previous techniques escape it. You need this more delicate result called Jordan's lemma to do that one. Anyway, is there anything else I wanted to tell you? Whoa, what's that? Roche's theorem. I think we're done. So do you guys have any questions about the course? You can